welcome to the stage Jalal Shatta.
Welcome back for the afternoon session. And on behalf of the ICM 2026 Organizing Committee, we welcome you back, where we'll hear the Laudatio honoring our prize winners. But before Hiraku introduces our esteemed colleagues, I would like to remind everyone of the rest of the program for today. The Abacus lecture is given by Cheyenne Ovis Sharna at 6 p.m., followed by the Simons Foundation reception honoring their co-founder, Jim Simon, where you will enjoy a mini documentary on his life and philanthropy, and hear remarks from Simons Foundation co-founder Marilyn Simon, President David Spergel, and friend and physicist Brian Greene. Now, please welcome back to the stage Nakajima Hiraku, who will introduce our speakers. Thank you.
Yeah, I am asked how to choose Laudatios speakers, and there are two important points. One is those Laudatios speakers must understand quite well the recipient work. This is the first condition. And the second condition is they must keep the secret until this ceremony. So they indeed, they really did this work quite well. But unfortunately, I don't want to say something like that. Anyway, please join me welcoming to the stage our esteemed colleagues who will honor our Fields medalist. Gigliola Staffilani, who will honor Fields medalist Uden. Yasha Eliashberg, who will honor Fields medalist John Pardon. Jonathan Pillar, who will give remarks on the achievement of Jacob Zimmerman. Chris Soge, who will honor Hongwan. Julia? Yeah, you.
So while I wait for my slides to come up, I wanted to thank everybody for being here today, and I'm incredibly thankful to be given the Laudatio for Yudeng, who I met when he was an infant, I guess, mathematically, since he was a junior at MIT. So now the work looks like it's not going forward, the slides. Okay, so I guess it's so Yudeng has an incredible large body of work, and it was very hard for me to both make this talk accessible to everybody, but I promised that I kept secret from everybody that was given the Laudatio, including my husband, who learned just a couple of days ago. So I picked 3 topics from his work, and the first one is it's hard to point and via the microphone. Anyway, the invariance of the complex measure of phi p2. Don't worry, I will explain what that is, both for the nonlinear Schrödinger equation flow and also for 2-dimension and for the wave flow. Then the second work that I would like to talk about briefly is the rigorous derivation of the Boltzmann equation for a long time. And unfortunately, I will not do justice to this part because it was much better explained in the video that you watched, but I will repeat some of that. And finally, also rigorous derivation of the four-wave kinetic equation. Now, just to start with something simple. Let's look at finite dimension, and we're going to look at, I'm not sure where the pointer is. Anyway, so if I point here, you don't see it, right? No, there is no pointer. Well, I cannot use that because otherwise I can use the microphone. By the mouse, no mouse? Okay, so there was no mouse. I apologize. So let's try to see. I'm the first one. So this is what you get when you are introducing. So this is a finite dimension Hamiltonian system. And H is the Hamiltonian. And as we know, the Hamiltonian is invariant, does not change in time when you have an Hamiltonian system. This is finite dimension in the sense that the index n here is finite. And so if you count the variable Qn and Vn, they actually all live in R2 to d plus 1. What's important to remember is that it's finite dimension. We also know, thanks to the Liouville theorem, that the flow map is going to leave the volume measure invariant. What that means is that if mu is my volume measure, the Lebesgue measure if you like, and I take a set A, which is measurable in finite measure, then if phi t is the flow map, then the measure of A is exactly the same as the measure of the flow of the set A. Now, we can construct another measure which is also invariant, which I'm going to call the Gibbs measure. And this is the volume measure multiplied by e to the minus beta. Beta is usually called the inverse of the temperature times the Hamiltonian. And this is also invariant because the volume was already invariant and the Hamiltonian is. Now, there is a way of looking at a system which has infinitely many, well, the dimension is infinite. This is in the following way. So this is the Schrödinger equation. I is the complex I, partial derivative in t, and the Laplacian. A u is a function that takes values from time r, and then space variable is periodic. So I'm going to think of it in the torus, and it's complex valued. And let's assume that this is a non-linear problem. So there is a power here, and the power is p minus 1, and p is integer and even. Now, if you take the Fourier transform of the solution u, this has a real part and imaginary part. And if you write the functional h of u with the kinetic energy and the potential energy, you can actually recast the whole equation as a Hamiltonian system. But different than before, n is no longer a finite index. This is running in ZD if I am in dimension d. So this is an infinite dimensional Hamiltonian system. So now the question is, can you come up with measures such as the Gibbs measure that I mentioned before? Well, there are question one. So can we define some measure that looks like this? Of course, this seems not to make any sense whatsoever because the volume is not finite. But let's just write it like that. And then if we can make sense of this measure, can we make sense of a flow map that lives on the support of this measure? And if we do make sense of this flow map, can we prove that this measure that let's assume we can define is invariant with respect to this flow map? So this is now an infinite dimension version of what I showed you at the beginning. Well, the answer to question one is yes. And in fact, there are many, many people, most of them in probability, as you can guess, that tells us when this type of measure here can be defined. And I'm not going to go into details, but there is a name for that. This is called the Gibbs measure phi PD. P is related to the nonlinearity. D is related to the dimension of the problem. This can be defined when d is 1 and 2 for any p, even greater than 2, and also for d equals 3, dimension 3, and p equals 4. Okay. So now we answered the first question, and I mentioned the people that have worked on this work, on this question. Now we want to answer question 2, whether we can construct a flow map that is in the support of the measure. Well, I'm not going to say much except for the fact that for people that are expert in this field, this is how it looks. I wanted to give you an idea how it looks, the typical element in the support of these measures. So this is the basis for my Fourier system. And this is, you can think of this to be the Fourier coefficient, and Gn omega is an IID complex random variable. Now, as people working in PD, like Yudeng was at the beginning when he came to ask for a question for his summer program, what we tend to look at is the regularity of the set of the initial data in order to claim whether there is a flow or not. And unfortunately, if you try to calculate the regularity of this typical element, it's very low. It's 1 minus d over 2. So for example, in dimension 2, it's not even a function, it's a distribution. So the question of whether the flow exists is not a simple one. Okay, so let's see. Okay. So now the low regularity makes, as I said, define the flow difficult. And in fact, Bourgain in 1996 answered this question. So with probability 1, renormalize an LS. So I wrote before a nonlinear Schrodinger equation with a certain nonlinearity p minus 1. You have to modify the nonlinear part. You have to renormalize. I'm not going to go into details, so it has to be changed a little bit. But for that equation, in dimension 2 and p equals 4, meaning cubic nonlinearity in the way I defined it, has a global in-time flow, so there is a flow, in the support of the Gibbs measure. And in particular, that measure leaves, that measure is invariant with respect to the flow. Okay, so this was the state of the art before the team, Deng, Namo, the UA in 2019 actually extended this proof of Bourgain to any kind of nonlinearity even. So now the phi P2 is defined for all nonlinear terms. Now, if for people who are familiar with more the stochastic PDE, this is the equivalent or very close to what Martin Hare and Gubinelli and all did for more parabolic type of problems. I want to just give a very brief, at least some idea of how the proof goes. Here, I apologize, it's a clicker that it's not simple to use. Okay. So on the top, I put what Bourgain did. So he's looking for a solution U, and the way he worked on the problem is separate the U into one part, which is completely linear but random, and then another part which turned out to be more regular. Then in the first work, Deng, Namo, the UA, they went much further in splitting the solution that you look for into, yes, a linear random, but there are other terms. So in fact, they introduced what they call the random averaging operator plus a piece which is more regular. So they had to do much deeper. And in order to complete the program, that was a year later, they wrote the solution even in extra more piece. I'm not going to go into details, but I wanted to say that this actually now has a name. They call the random tensor. So there are more applications than just in this case. Okay, so the next part, you watch the video or the field medalist video, and you learn that one of the main problems that was solved by Yudeng and Zahir Hani, and I will mention before also Ma, is the derivation of the Boltzmann equation for a long time. So briefly, what does that mean? So imagine this box has a fluid, has a gas in it. So these are the particle, the gas. And in the video, you saw that you can think of the molecule interacting with each other, just like, for example, in 2 dimensions, the balls in a billiard. Okay. Now, we are not interested on the specific trajectory of each molecular. That's not important, and it will be, the number will be very much big to look at. So what we are interested is in how the density of this fluid, this gas is going to behave. So think of the number of particles to be n, and epsilon, for example, the radius of the molecule. So there are certain relationship between n and epsilon, let's call it alpha. In fact, this is the case in the Boltzmann grand scaling limit. And now we take n goes to infinity, let epsilon go to 0, and we should come up with this equation. Now, many people worked on this problem, both from a more theoretical point of view or a more formal kind of view. So here I have put many people sort of in time evolution in a sense. And in all these works, the problem is approached in a perturbative setting. And in fact, what you then explain in this video is the enemy of taking this limit is the fact there might be a recollision and how you keep track of that, even from a probabilistic point of view. That's the reason why all of this work is for short time. Let's see. Okay. But in 2025, Deng, Hani, and Ma proved that the Boltzmann equation from hard spheres dynamics can be derived for arbitrarily long time with the assumption that the equation itself has a solution. Now, this is an incredible important step in a much larger program, which here schematically, and I borrow this from Deng's slides, schematically tells you what kind of limit you want to take. So there is so-called microscopic situation, that's the particle, that the gas in the box. Then there is a mesoscopic scaling, that's the Boltzmann equation. And then taking further limit, hydrodynamics limit, you end up with hydrodynamics equations such as Navier-Stokes. And this is the macroscopic limit. So proving that you can, in this step, you can take a limit that works for large time is incredibly important. And by the way, I didn't mention this, but all of this is also very much connected with the Hilbert-Stokes problem. Okay. Now, in the picture that I gave before, we had particles with a gas, but you can also think that you might have a situation in which instead of interacting particles, you interact waves. This is a situation that could happen both in a fluid case, but also in quantum mechanics physics. So let's think of these guys to be little wave packets. Let's imagine that they are in a box of size L, and there is another parameter epsilon. So while in the example of the gas in a box, the balls were hitting each other like balls in a billiard, in this case, the wave packets are interacting with each other according with a certain dispersive equation, which we're going to assume to be the Schrödinger equation. But it's called weakly nonlinear, meaning in front of the nonlinearity, there is this parameter epsilon. So then what you want to do is assume that there is a certain connection between the epsilon, this parameter in front of the linearity, and L, which is the box. And then you want to take the limit as L goes to infinity and epsilon go to 0 and obtain what I call here an equation for the density of the energy spectrum. Now, physicists knew this equation here already. They had, they understand what the issue or the problem is, and they derived the equation by ignoring, let me just briefly say, ignoring everything that had a power in front, which was bigger than epsilon squared. The problem is that there are infinitely many of these pieces that have power epsilon to the k, where k is greater than 2. So physicists ignore it and got the equation, but if you want to have a rigorous derivation, you have to understand how this smallness and this large number of pieces is going to come about. And I wrote here a list, and then at the end, like in 21, 23, Deng and Hani finally arrived to the derivation in the right scale of time, which is called the kinetic time. But there was this tau here that was still small. So into 2023, they proved that this tau that it's used in derivation could be actually, again, arbitrarily large as long as the four-wave kinetic equation has a solution in it. Now, for Deng and Hani, the particle and the wave setting, and I'll give you an example of both, for the first time were perceived in a similar manner. The proof of theorem 3 and theorem 4 are different in a sense. They're unique in their own way, but they really share a fundamental approach. So I'm going to, in the last couple of minutes, just give you an idea what they do. And this is completely not fair because it's much, much more complicated. But anyway, So you take this large interval of time, you divide long time interval into layers, propagate carefully the sign ansatz for each ensemble, layer by layer. And this allows for the emergence of something which is reversible. By the way, the dispersive equation, such as the Schrödinger, is reversible. You can go back and forth. But when you do this process, you obtain the wave kinetic equation, the Boltzmann equation. They are not reversible. And they can see that in this procedure. And then capture this ansatz in a multi-layer diagrams, which can be analyzed using analytic estimates, cancellations, and in particular, an incredibly fine algorithmic argument. So this is my last slides. And I found the mind of Yu Deng to be incredibly able to contain a lot of calculation in it. But really what impressed me a lot and what distinguish him from other mathematicians, I guess, is no fearing the expansion to infinite order, all these pieces, just be courageous enough to look at them. And then when he looked at them, he's able to have this great intuition of finding cancellation, because when you have so many pieces, unless things start cancel with each other, it's very hard to handle. Mastering combinatorics and finding algorithms that reduce very large structure to small building blocks. And mastering, of course, beyond all of this, very hard analysis MPD. So I want to congratulate you, Deng, and I want to say that I expect even greater things in the future for him. Thank you.
Giuliano, thank you very much. Next is, Yasha, please start.
So it's my great privilege to give this laudation for John Pardon. So mathematicians are explorers of mathematical world. The greatest success often achieves those who search and discover fundamental basic structure underlying concrete problems. Such discovery may create entirely new theory while also resolving long-standing questions. John Pardon is one of these explorers. A key feature in his approach to mathematics is a systematic search for the right underlying structure. As he himself wrote in one of his recent papers, most of the real work has been in finding the right formalism, after which the proof fall into place with little resistance. So I'll begin with this, his first kind of early work on Gromov distortion of nodes. He himself talked about this in this video. And Gromov in 1983 asked the following question: is it possible to deform any node in the space, in the 3 space, in such a way that the traveling time from any 2 points from any point of the node to any other along the node is only finitely many times longer than traveling in the space? Gromov actually asked, is it kind of like maybe this ratio constant is maximally 100? So, and Gromov himself kind of showed that for a node, this ratio is actually equal pi over 2. And in 2004, so it's 20 years after, Elizabeth Denne and John Sullivan showed that for any non-trivial node, this ratio bounded below by something like 5.2, kind of 5 pi over 3. So by the time John came to this question, it was not known that maybe the best constant is 6 or something like this. But John proved that actually this is unbounded, and he showed that for torus node, and actually Gromov in his paper specifically asked if this is true for torus node to node, and he showed that for torus node, this number goes to infinity with this PQ, proportional to PQ. So I just want to also note that its precise value of the distortion invariant is still not known for any non-trivial node. So his next work was on Hilbert-Smith conjecture and also kind of his early time. And he proved the three-dimensional case of Hilbert-Smith conjecture that locally compact topological group, if it acts faithfully on some connected manifold, then G is a Lie group. In view of prior result, the Hilbert-Smith conjecture is equivalent to the claim that additive group of periodic integers cannot act faithfully on a connected n-dimensional manifold. John proved this claim for the case n equal 3. Previously, this was known only under additional regularity assumptions. Later, John returned to the subject of group action on three-manifold and resolved another long-standing problem by proving that every continuous section of finite group on a smooth three-manifold is a uniform limit of smooth actions. I note that in dimension 2, any continuous action is conjugated to smooth, and as John himself kind of showed in this paper, based on work of several other mathematicians, that the corresponding result in high dimension cannot be true. This pardon excursion to group action is in fact not kind of accidental pickup of some random problem, because it's a part of much larger product concerning moduli space of solution of elliptic free-form problem, which I will discuss next. So in one of his papers, John asked, what sort of mathematical object is the moduli space of solution to a nonlinear elliptic free-form partial differential equation? This question has motivated a large body of Pardon's work since his graduate year, the construction and reconstruction of foundation of the moduli spaces of solution to elliptic free-form problem, especially those arising in Gromov theory of holomorphic curves. In early 1980s, Donaldson pioneered application of moduli spaces of anti-self-dual connection, which are special solution of Yang-Mills equation, as a revolutionary tool in low-dimensional topology. Few years later, Gromov largely created the field of symplectic topology with his introduction of method of holomorphic curve, which are solution of another elliptic PDE, d-bar equations. Floer, Hofer, Taus, Foucault, and many others further developed the theory of holomorphic curve into powerful method into symplectic topology in application to Hamiltonian dynamics, low-dimensional topology in several other areas. In all this theory, and especially in theory of moduli space of holomorphic curves in symplectic manifold, it is transitionally considered necessary to achieve transversality, meaning that we want this equation defining this moduli space satisfy implicit function theorem, and therefore they are manifold or some kind of good object which we can study. It seems otherwise, in differential geometric context, it's really impossible to do with these moduli spaces because they could be just arbitrary closed set. Like the zero smooth function can be arbitrary closed set if we don't have any transversality assumption. Unlike, let's say, algebraic geometric context, when they are at least algebraic set and they are at least certified by manifold. How achieving transversality is not simple, and especially because on many symmetry constraints. So let me illustrate it by this trivial example. So if you want to construct generic paths connecting two points in the plane, then of course generic path does not pass through the origin. It's very easy to move this path out of the origin. But if you want this path to be Z2 equivariant, say certify gamma of t is equal minus gamma of t, then it has to pass through origin, you cannot move it. Several frameworks to deal with transversality issue, a construct what is called virtual fundamental classes, were developed. So Fukaya, Ono, and Fukaya, Otto, Ono, later McDuff, Verheim developed the theory of Kuranishi structure, which is like finite, local finite dimensional reduction glued together with some machinery. Hofer, Vysotsky Center developed, didn't like this idea of finite dimensional reduction and defined the whole kind of new functional analysis and what they call polyfold theory to deal with this issue. So what is kind of like characteristic for all these approaches that we do with kind of local charts, and then you have some gluing problem. And when you pass with one chart to another, you have to deal with smoothness of gluing map, and it always was very, very delicate. Pardon's approach, which he pioneered already in his PhD dissertation, and which was greatly developed and improved in his subsequent work, was to work directly with unperturbed moduli spaces and instead gluing together particular local perturbation and glue certain, instead of gluing particular local perturbation, glue certain derived algebraic structure associated with totality of all possible local perturbation. His method, which he called implicit atlases, allowed him to construct fundamental class using shift theoretic and homological method, and it required only topological gluing theorem, which was much less subtle and avoid all delicate smoothness issue. John himself demonstrated the effectiveness of his approach on construction quantum homology theory, and several other mathematicians used his approach to build foundation to other problems in symplectic topology. In his current work in progress, which is a 400-page unfinished yet book on his website, he further crystallized his description of moduli spaces, a solution of nonlinear Fred-Goldman equation, and their virtual fundamental classes as derived geometric objects. Doing this, he was building on the work of Serge and Grothendieck in algebraic geometry and using general derived geometry approach developed by Jacob Lurie and Toyin Vidzosi. In this framework, the finite dimensional reduction, factoriality, virtual fundamental class are encoded in the structure of the derived moduli object themselves. And while it's almost tautologically removes the subtle gluing question, it shifted the difficulty elsewhere to the problem of representability of the derived moduli functor. This problem was formulated explicitly by Joyce and solved by Pardon in his book. As John pointed out, related result independently were obtained by Pelle-Steffens. As we already mentioned, finite group action is intrinsically built into moduli problems. Because even in the best transverse situation, moduli spaces are orbifid, or in other words, locally are quotient of vector spaces by finite symmetry group. This creates a lot of problem, and according to this general principle of John Pardon, to deal with any problem, you first need to find correct foundational setup. And that's what he did in two papers, kind of foundational type. He constructed homotopy theory of finite, what we call Orbi spectra, and expanded to it classical topological result, top Androgyn top isomorphism, and its equivariant analogs. Here's just one of the corollary kind of it he proved on the way of building the theory. Namely, he proved that any finite dimensional smooth orbifold with bounded order of local isotropic group is global quotient of some manifold by unitary group, by some smooth action of unitary group. And this, of course, it was known for many special cases, but expert was kind of doubtful that this could be true in such generality. GPS does not stand for general positioning system, but it is referred to large work of Shil Ganratra, John Patton, and Vivek Chanda, which totaling more than 350 pages, whereas developed effective method for computing symplectic invariants of Weinstein manifold. Weinstein manifold are important building block of symplectic topology. They are symplectic analog of Stein complex manifold, which are affine complex manifold. And moreover, according to a theorem of Donaldson, which is an analog of Levshon theorem in projective complex geometry, any closed symplectic manifold with integral cohomology class has a codimension 2 symplectic submanifold whose complement is Weinstein. An important example of two-dimensional Weinstein manifold is a cotangent bundle of n-dimensional smooth manifold, and so this Weinstein manifold can be viewed as a neighborhood of zero section, which is Lagrangian submanifold inside this Weinstein manifold. A general Weinstein manifold could be thought as a neighborhood of possibly singular Lagrangian complex, which call it skeleton. Standard topological invariants, like homology, can be computed by partitioning the space into elementary pieces and then assembling global invariants from invariants of pieces and the information on how these pieces are glued together. Symplectic invariants arising in the theory of holomorphic curve a priori not of this type, because, for instance, to compute them, to define them, you need to know a lot of information about Hamiltonian dynamics on their boundary, about periodic orbit, and about holomorphic curve which converge to this orbit. The GPS main result provide what I would call combinatorialization of symplectic invariant and their kind of description in this standard sense of homology theory and kind of shift theoretic sense. So just to computing invariant for elementary pieces and then kind of like providing tool for gluing them together. This description is also important from the point of view of Kontsevich homological mirror symmetry conjecture, which claims isomorphism between a category of symplectic origin called Rep-Fukaya category and another category of complex geometric origin of a dual manifold called category of coherent shifts. And because GPS provided this shift theoretic description of the symplectic side, so now it became possible to verify this homological mirror symmetry by just verifying it locally and then to check that kind of assembly rule of the categories are the same in both sides. In the paper, Universally Counting Curve in Calabi-Yau three folds, John solved Molik, Nekrasov, Konkov, Pandaripanda conjecture in enumerative geometry, which related Gromov-Witten and Donaldson invariants for large classes of three-dimensional complex manifold, including Calabi-Yau three-dimensional manifold. In a Calabi-Yau manifold, which has a first-Chern class 0, virtual expected dimension of moduli spaces of any curve is 0. And so there is a classical problem of enumerating them. But enumeration is kind of like ambiguous problem because, for instance, Gromov-Witten invariants count equivalence classes of stable holomorphic maps, which mean parametrized curve, while Donaldson-Thomas theory counts algebraic subvariety, one-dimensional algebraic subvariety or subschemes. So even the word count is in fact kind of ambiguous because like this count can be, for instance, rational in Gromov-Witten case. So MNOP conjecture assembled this claim relation between generating function for this Gromov-Witten invariant and Calabi, Gromov-Witten and Donaldson-Thomason invariant by assembling them in some generating theories, like in the Gromov-Witten case, arranging them in the series according to Euler characteristic, and Donaldson-Thomas according to the holomorphic Euler characteristic, and then claiming that this partition function e to the Gromov-Witten series is the same as this Donaldson-Thomas up to some normalization and change of variable. So Brian Pandaripanda and Akunkov Pandaripanda proved that this is true in locally, so near one smooth curve. And Pardon found a striking way to reduce the general problem to the local one. He defined what is called Grothendieck group of one cycle on complex 3 manifold, whose element could be roughly identified with curve enumerative problem for 3 folds, while each theory, for instance, Donaldson-Thomas and Gromov-Witten, provide homomorphism of this group to numbers. And what he proved that this Grothendieck group generated by local enumerating problems, and hence local result implies the global one. Beyond finding correct universal setup, a central part of his proof was certain universality argument. And he also solved it ingeniously. I have to finish, I don't have time for this. So let me just say that John Pardon's mathematical interests are extraordinarily broad, and his research continues to branch into new areas. And I'm confident that he will continue to surprise the mathematical world with unexpected new ideas and discoveries. Thank you.
Thank you very much, Yasha. So Jonathan, please, the floor is yours.
Yeah, so hi, everyone. It's my honor to say some words about the work of Jacob Zimmerman. Jacob is a brilliant mathematician who has made major contributions across a wide swathe of fields, including arithmetic geometry, Hodge theory, algebraic geometry, and number theory. This talk is about the work of Jacob and not about working with Jacob, but I just want to say what a pleasure and privilege it has been for me to work with Jacob for 15 years now. And beyond his brilliance, he is a wonderful collaborator, and working together has been immensely enjoyable. For lack of time, I will address only Jacob's contributions around the André-Oort conjecture and in Hodge theory. Oh, right, so to introduce the André-Oort conjecture, I will set the scene with Diophantine geometry, which in the first instance studies the rational points, that is, points with rational coordinates on an algebraic variety, which is a set in complex space defined by polynomial equations. There are many questions one can ask. A convenient general question for my purposes is, which algebraic varieties can have a Zariski-dense set of rational points? The Zariski density means that there is no additional algebraic equation that captures all of the rational points. If there were, we could move our investigation, we could impose that extra condition and move to some smaller algebraic subvariety. When V, the variety is one-dimensional, a complex curve, Zariski density of rational points is the same as having infinitely many of them. And the answer to the question, famously conjectured by Mordell in 1922, was proved by Faltings in 1983. And the answer is that on a curve of genus 2 or higher, there can be only finitely many rational points. So they're simply not, they can't be Zariski dense. Faltings went on to answer the same question for arbitrary subvarieties of abelian varieties. only cosets of abelian subvarieties by rational points could have a Zariski dense set of rational points. Now, an abelian variety is a group variety, and it has an abundance of torsion points, which are points of finite order in the group. And now one can ask which subvarieties of an abelian variety can have a Zariski dense set of torsion points. Raynaud proved the theorem conjectured by Manin and Mumford. Only cosets of abelian subvarieties by torsion points have this. Now, for general varieties of dimension 2 or more, the original question about Zariski density of rational points is wide open. Now, the André-Oort conjecture is an analog of the Manin-Mumford conjecture for Shimura varieties and their special points. A Shimura variety is a very particular kind of algebraic variety. It's a moduli space parametrizing suitable objects. For example, it might parameterize abelian varieties of some suitable dimensions. If positive dimensional, it has an abundance of so-called special points, and these are the points that correspond to the suitable objects with maximal extra symmetries. They are algebraic points with rich arithmetic properties, and one can ask which subvarieties of a Shimura variety can have a Zariski dense set of special points. The André-Oort conjecture proposes the answer only on special subvarieties, which are essentially Shimura subvarieties, and which do indeed have Zariski dense special points. André himself proved the first non-trivial case in 1998, but subsequent results were conditional. They led to a full proof conditional on the generalized Riemann hypothesis by Klingler, Ulmo, and Yafaev. The point counting strategy employs rational point counting results for definable sets in O minimal structures. And so it relies heavily on ideas from model theory, which I won't go into. Jacobs, the movie, had a beautiful pictorial description of O minimality, and which we'll come back to later. But the key point about this strategy is that it reduces the André-Oort conjecture for a given Shimura variety to 4 discrete ingredients. And I will focus on the geometric ingredient and the arithmetic ingredient and Jacob's contributions to them. By the work of many people, spearheaded by Jacob, this led to a full unconditional resolution of the André-Oort conjecture in the period 2011 to 21. Now, the geometric ingredient concerns the uniformizing map of a Shimura variety. A Shimura variety is uniformized by a Hermitian symmetric domain by a map which is invariant under the discrete action of an arithmetic group. The simplest example of this is the J function, the modular function, which maps the complex upper half plane to the complex line. A Shimura variety known as the modular curve, which parameterizes elliptic curves up to isomorphism over the complex numbers. And the Cartesian powers of that setup. The paradigm example is the uniformization of Siegel modular varieties, which parameterize abelian varieties of a given dimension by the Siegel upper half space by the map given by automorphic functions. But a prototype example for what I want to describe, though it's not a Shimura variety, is the complex exponential map and its Cartesian powers. The functions giving these maps are non-algebraic. They're transcendental maps, but we need to know that they strongly avoid everything algebraic. And in particular, what we need to know is that the graph of these maps intersect algebraic subvarieties only in the expected dimension, never higher, except for clearly delineated exceptions, which, of course, are connected to the special subvarieties. The prototype result is known as Ax-Shanwell, and it's the result of this form for the exponential function and its Cartesian powers. And this theorem, which I'm not going to state, I'm simply going to say that it is a functional version of Shanwell's conjecture on the transcendence of the values of the exponential function. And that conjecture is written on the slide. And those numbers, too, are conjectured to be as transcendental as possible, given the functional equation satisfied by the exponential function. And I want to say also that only a special case of Ax-Shanwell is needed to prove André-Oort, but the full statement is the natural one and useful in generalizations. These results were established over the period in increasing generality by Jacob and collaborators and others, culminating in the proof of a functional version of André's generalized Grothendieck period conjecture by Baker and Zimmermann. The period conjecture asserts that the integrals, it's again a conjecture about numbers. It asserts that the numbers given as the integrals of algebraic functions over semi-algebraic domains, things like the area of a circle, are as transcendental as possible. And on this conjecture, see the beautiful article Periods by Kontsevich and Zagier. André's version of the conjecture includes Shanwell's conjecture as well, and the Baker-Zimmermann functional result includes all the previous formulations in Shimura and Hodge settings. So now I want to switch to the arithmetic ingredient that is needed, and that is that the Galois orbit of a special point is large. So I've described this in the sentence in purple on the slide, and then also a version with quantifiers for each Shimura variety. There exist these two constants, and so on. So the Galois orbit is supposed to be large relative to the discriminant of the special point, and that means at least some fixed positive power. And the prototype for this result is a very classical result of Landau and Siegel from the 30s, generalized by Brouwer, on the size of the class number of an imaginary quadratic number field. So there on the slide is the prototype result. So for the J function, the Galois orbit of a special point corresponding to the ring of integers in an imaginary quadratic field is in bijection with the class group of the field. And the classical lower bound for the class number, which is the size of the class group, in terms of the discriminant of the field, which is the discriminant of the special point in this case, is exactly the shape of the bound needed. So there on the slide you have, well, the Brouwer, the Landau-Siegel class number estimate. These results were established in 3 waves. First, Jacob proved them directly for the Siegel modular varieties up to dimension 6. That dimension is the dimension of the abelian varieties being parameterized in his paper, Brouwer-Siegel for arithmetic tori. The proof for all Siegel modular varieties went a different way. It went via something called the Faltings-Height of a special point. Using the isogeny estimates of Masse-Wustholz, one can show that if the height is small relative to this discriminant, meaning discriminant negligible, then the Galois orbit is large. This height is explicitly predicted by a conjecture of Kolmez, which is still open, but average version of it was proved by two groups independently in 2021, and the average version somehow sufficed to conclude this pathway. Now, the third step was the general Shimura variety, and there one does not have isogeny estimates, nor a Faltings-Height, nor a Kolmez conjecture. But here, a sharp point-counting result due to Binyamini, Schmidt, and Yafeev again reduces the problem to proving that the Weil height is discriminant negligible. And Jacob and co-authors established this in 2021 by defining an almost canonical height on the special points. And in each case, this arithmetic ingredient completed the proof of the André-Oort conjecture. Now, Hodge theory vastly generalizes the picture of Shimura varieties. Over a family of algebraic varieties, integrating suitable differential forms, one gets the period map, taking a variety in the family to its periods, which are some numbers that move in the family. The Shimura variety case is a special case in which the image of this map, modulo its monodromy, is itself an algebraic variety. So here I will be even more brief describing Jacob's fundamental contributions, but I can recommend that people go to the talks by Ben Baker and by Jacob at this Congress to hear more. So with collaborators, Jacob proved definability of period maps of variations of mixed Hodge structures. And here definability means in an O-minimal structure. This establishes a strong tameness of these maps that can be powerfully exploited. In particular, to reprove the fundamental theorem of Catani, Deligne, and Kaplan, establishing the algebraicity of the Hodge locus, and to develop an O-minimal Gaga, paralleling the classic Gaga of Serre, and further applying these tools to make fundamental advances, in particular proving a 50-year-old foundational conjecture of Griffiths. So Jacob has made several other deep contributions in a range of areas that I won't go through. And at this point, just say congratulations, Jacob, on your wonderful results. Okay, thank you.
Thank you very much, Jonathan. Chris, the floor is yours.
Very happy to be here celebrating Hong Wang and the other field smellists. So Hong has several remarkable results in harmonic analysis and geometric measure theory, including the resolution of the Kakeya conjecture for R3, resolution of the local smoothing conjecture for the wave equation in 2 dimensions, and major advances on related problems concerning the Fourier transform, namely Stein's restriction problem and the Bach-Norris problem. She also resolved the Furstenberg set conjecture. Each of these 3 conjectures was decades old. Today, I'll give you a high-level overview of Hong's work on the Kakea conjecture and the other principal problems that are related to the Fourier transform. So the things in items 1 through 3. Later in the Congress, she'll be talking about the Furstenberg set conjecture and related problems. So let me start by setting the table before I go over Hong's results on the Kakea conjecture by going over some background. So for over a century, there's been much interest in Kakea sets. A Kakea set is a compact subset K of Rd containing a unit line segment in every direction. And a very old problem dating back to 1917 asks, how small can these Kakea sets be? In 1917, the very same year, Kakea and Besekovich began the study of this question for different reasons, and they were completely unaware of each other's results for many years. Remember, 1917 was the year of the Russian Revolution, so Russian mathematicians at the time were fairly isolated. So Besekovich didn't know about Kakea's work, and mathematicians outside of Russia did not know of Besekovich's work, by and large. Besekovich was working on a problem in Riemannian integration, and he realized that he could produce a counterexample to this problem if he could construct very small planar Kakea sets. Kakea, on the other hand, proposed the Kakea needle problem that many of you have heard of. It asks you to find the planar set of smallest area in which a unit line segment can be continuously rotated through 180 degrees without leaving the sets. Kakea called these sets revolvable sets. In Kakea's paper, he gave 3 examples. Obviously, a disk of diameter 1 is an example. Also, a small area is an equilateral triangle of height 1, and a set having even smaller area is the deltoid of height 1. Kakea conjectured that the deltoid should be the solution of the Kakea needle problem. Deltoids might not be so familiar to you. However, when you take a 3-point turn in your car is basically sweeping out a deltoid. So it was a natural guess for the solution of the Kakea needle problem. On the other hand, Besekovich showed that you could do much better for both problems. He constructed Kakea sets of 0 measure in a 1919 paper. That paper has basically been lost to time, by the way. It was published in an obscure Russian journal, which went defunct after just publishing 2 volumes. So in 1928, he republished his construction, and he gave the simple modification of a negative solution of the Kakea needle problem. Remember, he wasn't aware in 1919 of this paper, of this problem. So he showed that there are planar revolvable sets of arbitrarily small area. Next, let's fast forward 50 years to the remarkable work of Charles Pfefferman establishing a relationship between Kakea sets and Fourier analysis. Pfefferman was working on another old problem. If f hat is the Fourier transform, do the truncated Fourier integrals Sn of f converge to f in LP, where the truncated integrals Sn of f are defined in the Fourier integral next to the big green question mark. Note that if the integration were over all of Rd by Fourier's inversion formula, this would just be a formula for f. Also note that if you take the transform of Sn of f, you obtain f hat times the indicator function of the ball of radius n. For this reason, they're called ball multiplier operators. It's easy to see, using Plancherel's theorem, that there is L2 convergence. Sn of f converges to f in L2, so it works for p equals 2. In the 1920s, Marcel Ries showed that in 1 dimension, there's LP convergence for all possible p's between 1 and infinity. Okay? But on the other hand, remarkably, using Besekovich's construction of these 0 measure Kakea sets, Pfefferman proved the striking ball multiplier theorem, which says that in 2 or more dimensions, there's only LP convergence for p equals 2, which is a trivial case. In his paper, Pfefferman wrote, "It's an unfortunate fact." So we conclude from his construction and later developments that there's a striking deep connection between properties of Kakeya sets and fundamental properties and problems in Fourier analysis and PDEs. So we don't like unfortunate facts. And Pfefferman's argument teaches us that it's important that Kakeya sets are not too small. If they were, the major conjectures in Fourier analysis would just crumble. So that brings us to the Kakeya conjecture. If D is larger than or equal to 2, and if K is a Kakeya subset in RD, the conjecture states that the dimension should be full. So either Minkowski or better yet, Hausdorff dimension. Hausdorff dimension is always less than or equal to Minkowski dimension. So it's a stronger result, of course, if you can show that the Hausdorff dimension is full. I'll recall the notion of dimension soon when I discuss Hong's discrete Kakeya estimates. So the Kakeya conjecture was verified in 1971, the same year as Pfefferman's paper, by Rory Davis. He showed that in 2D, Kakeya sets have to have full dimension. So now, 50 years basically after Charles Pfefferman's paper, we have our third milestone in the Kakeya story. It's the remarkable result of Hong Wang and Joshua Zoll verifying the Kakeya conjecture in 3D. So of course they showed that if K is the Kakeya subset of R3, then it has to have full Hausdorff dimension. So that resolves a decades-old conjecture. And finally, after many, many years, more than a half century, one of the principal conjectures in harmonic analysis that's related to the Fourier transform, I'll go over the other ones in a second, has been resolved in a dimension larger than 2. Okay, and there were, and as I have to quote Netz Katz says, it's a once in a century kind of result. So there are many earlier results by leading figures in harmonic analysis over the last, say, 35 years. Bourgain, Wolf, Laba, Katz, and Tau, and Katz and Zoll. And basically they were stuck at 5 halves, 2.5. So Wolf in 1993, in a very important paper, proved that Kakeya sets, subsets of R3, have dimension 2.5. And these were improved just a little bit by Laba, Katz, and Tau, and by Katz and Zoll. 5 halves plus epsilon naught, and Terry Tau likes to joke that you can take epsilon naught to be 10 to the minus 10. It's a pretty small number. Okay, let me give you a rough outline of the approach of Wang and Zoll. So in order to show that Kakeya sets of subsets of R3 have full dimension, they reduce to a problem of obtaining lower bounds for unions of tubes, delta tubes. So a delta tube, where's my Apple Pencil, is a 1 by delta cylinder. Okay, delta is very small. And as we'll see in just a second, these discrete Kakeya estimates yield the dimension bounds. Now they have a remarkable argument for proving these discrete Kakeya estimates. They use multi-scale analysis and they set up a self-improving iterative scheme. And in a nutshell, what they're able to do is they start with the trivial estimates, say that the dimension of Kakeya subsets of R3 are always 2 or more. Then after one iteration, they can improve that, say to 2.1, then maybe after 2 is 2.15. And what they end up showing is that given any number smaller than 3, after finitely many iterations, Kakeya sets must have dimension larger than that number. And that, of course, means that the dimension is full. It's really an incredible argument. So here are the discrete Kakeya estimates of Wang and Zoll. Pretty simple. So if T is a collection of delta tubes, so again, those are cylinders of length 1 and radius delta. So if T is a collection of delta tubes in R3 with delta separated directions, then they show that the volume of the union of the tubes for any epsilon must be bounded from below by a multiple of delta to the epsilon times the number of the tubes times the volume of a single tube. Now note that if the tubes were disjoint, the blue term in the right would have to exactly agree with the blue term in the left. The volume of the union would be the number of tubes times the volume of a single tube. So since they proved this estimate for all epsilon, it's really saying that direction-separated tubes can't intersect too much. And it immediately implies the Minkowski dimension. Okay, so if you consider a delta neighborhood of a Kakeya subset of R3, then since it contains a line segment in every direction, it's a simple exercise to see that this discrete Kakeya estimate implies that the volume of that delta neighborhood must be bounded from below by a multiple of delta to the epsilon for every epsilon, and that exactly means that the Minkowski dimension is 3. They prove a more technical variation on this estimate to show that the Hausdorff dimension also must be full. Okay. So I won't be able to tell you the multi-scale arguments that they use, quite involved, but I can show you a picture. So here you see Hong telling us about how they're using the distribution of small delta tubes inside of slightly larger tubes. And it might be hard to see, but she's also telling us in this lecture about how they use the structure of these tubes within very small balls to obtain the estimates that she's pointed to. There are many, many other cases, but if you want to see more details about this wonderful work of Wang and Zal, I refer you to Joshua Zal's lecture on the 28th. He'll be speaking about this in more detail than I can. Okay, let me conclude by telling you about the other really important results of Hong Wang on this family of conjectures that's related to the Fourier transform. Quanta magazine has an article about this. They call this a tower of conjectures that rests upon a needle. Hong, by the way, has been keeping the writers of Quanta magazine quite busy. They have several very nice articles about her. So before I tell you about the tower part of the title, the catchy title, and the needle part of the catchy title, let me explain the conjectures. So the first conjecture, the local smoothing conjecture for the wave equation, is a conjecture that I formulated way back when in 1991. And it's just about optimal LP space-time, local and time, regularity estimates for solution of just the Minkowski wave equation, the flat wave equation. Next on the list is a conjecture dating back to the 1950s. It's the Bachner-Reis conjecture. It's about optimal LP estimates for family of operators generalizing the Ball multiplier. Pfefferman's construction shows that the Ball multiplier operator is not bounded on any LP besides P equals 2. So you have to consider other operators, and the ones that you consider are called the Bachner-Reis operators. Next on the list is Stein's Fourier restriction theorem, or conjecture rather. It's about the optimal range of exponents P for which f hat, the Fourier transform of f, restricts as a function to the sphere when f is in LP. It obviously does for P equals 1. The Fourier transform of an L1 function is bounded and continuous, so it'll restrict to anything. It doesn't because of Plancherel's theorem for P equals 2, and Stein's conjecture is about the optimal range of exponents for which you have this restriction phenomena. And then last on the list is what I've been talking about before, the Kakeya conjecture. Okay, why is it a tower? Well, it's pretty straightforward to see that the local smoothing conjecture implies the Bachner-Reis conjecture. The Bachner-Reis operators and the solution operators for the wave equation are just related by the Fourier transform. So just by an application of Holder's inequality, you can see that the local smoothing conjecture implies the next one down on the list, the Bachner-Reis conjecture. Harder, and this is due to Terry Tao, is that the Bachner-Reis conjecture implies the restriction conjecture. Another hard case is based on a nice multi-scale argument of Bourgain, is that Stein's Fourier restriction conjecture implies the Kakeya conjecture with the Hausdorff dimension. Okay, so that's the tower part. And obviously the needle part refers to the Kakeya conjecture at the bottom. If the Kakeya conjecture were false, then the whole tower would have to collapse. So it's really important to understand the Kakeya conjecture. I'd also like to point out that in 2 dimensions, everything but the local smoothing conjecture was fully resolved in the 1970s. The local smoothing conjecture wasn't solved until recently, but establishing partial results led to partial results for the local smoothing conjecture led to the development of decoupling theory. which is a very important new tool in harmonic analysis with many applications. So my last slide about Hong's work is her work on these conjectures. Well, as you probably guessed, she's, with her collaborators, Larry Guth and Ruijing Zhang, solved the local smoothing conjecture in 2 dimensions. That was the only conjecture that was not fully understood since the 1970s in 2 dimensions. And of course, I've been telling you about how Wang and Zoll fully resolved the Kakeya conjecture in 3D. She also has the best known results for the other 2 conjectures. For Stein's restriction conjecture, starting with her PhD thesis under Larry Guth in 2019, she had the best restriction conjecture estimates, and that's been improved more recently in work with Xiaokun Wu. She also has the best known results for the Bach-Norris conjecture. That's work with Xiaoming Guo and Ruijing Zhang. So at long last, Hong and her collaborators have finally closed the door on 2 dimensions, solving the local smoothing conjecture in 2D, and they've also finally opened the door to higher dimensions. It's really an important results. So with that, I'd like to say congratulations to Hong and thank you for your attention.
Thank you very much, Chris. So let us thank all 4 Laudatios speakers in this afternoon. Thank you very much. Now it is the time for coffee. Please make your way out to the terrace ballroom pre-function space for coffee and snacks. But don't go far. We will return here in 30 minutes to hear the rest of our Laudatios. Okay, let wait us a little bit more because still people are working. Yeah. Please take seat. We'll start soon.
Welcome to ICM 2026. Our program is about to begin. Please silence all cell phones and take your seats.
Yeah, please take seats or we'll begin soon. Okay, let me start. So welcome back. We will now hear our colleagues' honor, those who have received honors presented in the second part of this morning's program. Please join me welcoming to the stage our esteemed colleagues who will honor our 4 award and prize winners. Daniel Spielman, Laudator for Abacus Medal winner, Cheyenne Ovis Garland. Dan Fried, Laudator for Charm Medal Award winner, Graham Siegel. Stefan Light, Laudator for Gauss Prize recipient, Yuri Nesterov. Carolina Vivian Shelnip, who will honor Hannah Fly, recipient of the Leila-Bati Prize. Dan, please. Floor is yours.
Thank you. For the last 16 years, I have had the pleasure of reading papers by Cheyenne Oves-Garan. His work has been remarkable for making progress on problems in which the field has been stuck for decades, for bringing new insights into the problems that we study, and for introducing techniques that are now being applied throughout the field of algorithms. And I'm very happy that today I can share with you my enthusiasm for his work by explaining, well, 2 of the things that he has contributed to. The first one I would like to tell you about is the theory of sampling problems. So in a typical sampling problem, you're given a description of a set, let's call it S, and you would like to find a random element of that set. Usually a uniformly chosen random element, maybe from a different probability distribution. But you should think of it as a very large set with a very short description. The way people usually solve this problem is with a method called Markov chain Monte Carlo, or you can think of it as a random walk. The approach begins first by finding some element of the set S. You've got to be able to find some element to get started. And then we need to be able to transform an element of the set S into another element. Ideally, we should be able to transform the element into more than one so that we can inject some randomness into this procedure. If we can transform an element of the set S into another element, we will pick one at random that we can transform it into. And then we iterate. Given an element, we transform it at random into another element, maybe another nearby element, and we keep repeating this. And in the cases where we apply MCMC, we know that if we do this for long enough and stop and output the element that we're at, it will be uniformly random or very close to uniformly random. And this procedure is applied all over the place. I've gone to talks in numerous departments where people apply MCMC algorithms. I listed a few fields where people use this, like statistical physics, Bayesian statistics, finance, computational science, some computational social sciences, and machine learning. But there's been a problem in the way people use this, which is that it's in the part where I said eventually you can stop. You run this procedure for long enough. There were almost no formal bounds on how long was long enough. So what were people doing in practice? They maybe have some diagnostics that they check and they think, if this diagnostic is satisfied, then I've probably done this for long enough. Or they were hoping that they had done this for long enough. But if you were trying to use this procedure and you really want a random element, and then you're going to make some downstream analysis or use it to make a decision, you don't want your analysis to rest on hope. You want it to rest on theorems. And that's what Cheyenne has provided with us. So I'll tell you about one of them first, which is about the problem of sampling a random basis of a matroid, where he and his co-authors proved the Mihail-Vazirani conjecture from 1989, which essentially says using MCMC solves this problem and quickly gets us a random basis of the matroid. Now, I'm not going to tell you what a matroid is. Instead, I will tell you 2 things that it generalizes, and those things I can tell you what they are. The first thing a matroid generalizes is the set of random spanning trees of a graph. So if you have a graph, like I drew on the left, a spanning tree is a subgraph. It contains all the vertices, but only some of the edges. It should be connected. So between every pair of vertices, there should be a path going through the edges you've got left, but only one. There should be no loops, or no cycles. So in the middle of the column, I drew two graphs that are spanning trees. And on the right, I drew two that aren't. The one at the top isn't because it's disconnected, and then the bottom isn't because it contains a cycle. So if you have a spanning tree, you can get another spanning tree in a pretty easy way. First, remove an edge. The one in the middle at the top, I removed this edge that I shaded in red. If you remove that edge, you can then think of adding back another edge to make it disconnected. Not all of the edges will work. One of these edges, if I add back, I get a cycle, but the other edges are okay. So pick a random one of those edges to add back, and now you've modified your spanning tree. And you can keep iterating this procedure. Okay, here's the other structure that matroids generalize. Independent sets of vectors, or bases when you take enough of them. So let's say I give you a list of vectors. Like here, I've given you 5 vectors. I called them A, B, C, D, and E. And now I ask you, well, if I ask you just to find a basis, that's easy. You can use linear algebra to do that. But what if I ask you to find a uniform random basis? I promise not all triples of these vectors are bases. Well, what you do is find one basis. You know how to do that. And the first 3 vectors here, A, B, and C, are a basis. Then if you're applying the MCMC procedure, you will drop one of them at random. Let's say my first example, I dropped C. And then you can add back another at random to still get a basis. I added back D, and then you can drop one at random. I dropped A, and then add back one to get a basis. You add in E. If you keep doing this, we now know by Cheyenne's results that you eventually get a random set of vectors that give you a basis. And I will tell you a little bit now about how that result is proved. First, we're going to look at it as a graph. In this graph here, for every node, I have labeled it by the sets of vectors that correspond to a basis. You'll notice I have triplets. There could be 10. There are only 8. So only 8 sets of those triplets corresponded to bases. I put an edge between 2 of them when you can get from one to the other by dropping an element and adding one back. So those are the steps we can take in our process. The arrows from ABC to ABD and from ABD back down to BDE that I drew, those are the steps that I showed you in the previous slide. So Mihail and Vazirani conjectured that this graph is an expander, and they gave conjectures on its eigenvalues that control the mixing rate, and that would guarantee that this random walk on this graph mixes quickly. And in the paper Log Concave Polynomials 2, Nari, Liu, Ovescaran, and Vinzant proved the Mihail-Vazirani conjecture. So we know that now that this graph is a good expander and the random walks mix quickly. They really did more than that. They got very sharp bounds on the eigenvalues of the matrix underlying this random walk, and very sharp bounds on its expansion. And I just want to tell you why this is amazing to me. Many people worked on this problem. We would have been very happy to prove much worse results. But this was the first significant result on this problem, and it was sharp, which was amazing. I should also tell you a little about how they prove it. So you can gather from the title, there's going to be some polynomials involved. I'll tell you about that. But first, I want to tell you about the theory, another theory they used, which came out of this recently developed theory of high-dimensional expanders. And that's really one of the key ideas they introduced. So to explain that, I want to describe the simplicial complex of independent sets. So we're going to take that graph, I'm going to push it to the top, and I'm going to drop it for a moment. We're going to add in all subsets of the vectors that are independent. We'll arrange them level by level. The higher levels have more vectors. And I've put edges between them, which hopefully you can see, that show when one set is contained in another. What we're going to study in this simplicial complex are the links. So a link is determined by a subset, or one of the things that appears here. Here I'm showing you the link of just the singleton set that just contains B. And then the link is all subsets that contain S. And we take a look at the structure induced on them. So those are the ones I've all shaded in purple. Then we're going to look at the graph of a link. So the vertices of the graph of a link are the sets that are just one larger than S. So you add one more element. So here, those are all elements labeled with 2 vertices. If I'd drawn a bigger thing, they could sit at any level in this picture. The edges appear when if you go from one of these vertices up a level and down a level, and those will give you the edges that you have. So whenever 2 nodes appear in a node at a higher level. Okay, an important thing to note, there are a lot of links. There is a link for every single subset that appears here. So every element of the simplicial complex, but the links are small. If I only have n vectors, each link can have at most n, the graph of each link can have at most n vertices. So what they do is employ a local to global analysis. They reason about all of these small links and use that to analyze the graph that we care about, the random walk-on at the top. And the way they do that is using the trickle-down theorem from high-dimensional expansion developed by Denur, Kaufman, and Oppenheim. So this theorem says that if all of the graphs of the links are 0 spectral expanders, I can't define that for you now, but just think very good expanders, then the walk that we care about on the graph, on the random walk on the bases, mixes rapidly. And it gives precise numerical bounds for that. Okay, log concave polynomials. What they do is they consider the generating polynomial of a matroid. So to define that, we need first to make a polynomial, we need variables. Let's introduce one variable for each vector. I called my vectors a through e. We'll call the vectors x, the variables x sub a through x sub e. For every basis, that is every subset of those vectors that's independent, we'll have a monomial. And the monomial is just, of course, the product of the variables corresponding to the vectors in that basis. So like we start with xa times xb times xc, that was the first one, and add in, there are going to be a total of 8 terms for the matroid we considered. Now, it's not a priori obvious that the generating polynomial of a matroid should be useful or have any nice properties. But it is, and it does. So in the paper Log Concave Polynomials 1, Anario, Vescaran, and Vincent proved that the generating polynomial of a matroid is strongly log concave. So to find that, I'll say a polynomial is strongly log concave first if its logarithm of the polynomial is a concave function on the non-negative reals. And we need the same is true for all of its derivatives. Then it's strongly log concave. And in the paper Log Concave Polynomials 2, where they were joined with Liu, they prove that if the generating polynomial of a matroid is strongly log concave, then all of the link graphs are 0 spectral expanders. And when you combine that with the trickle-down theorem from the previous slide, now you know that the random walks on the matroid mix rapidly. So this was a breakthrough result and one of the classic challenges, because matroids have so much structure. We figured we should be able to prove that the random walks on the mix rapidly, and now we know that. But they also have so much structure that people wondered, okay, will this breakthrough extend? And thankfully it does. So Anari, Liu, and Ovescaran introduced this technique called spectral independence, really pulling some ideas out of that other work and generalizing it, that gave us a very broadly applicable technique that can now be used to prove random walks mix and Markov chains mix and all sorts of applications. The one from their paper that I put up here was for what's called the hardcore model. If you're given a graph, you want to sample an independent set of vertices. These sets I drew in purple are independent. They're independent if they don't have any edges going between them. But they want to sample it with some probability exponential in the size of the set. And their work shows you can do that up to, well, it depends on the larger the base, the harder it is. they show us up to the right bound on the base. Of course, this was just one result. What I should emphasize is that since their paper was written, it feels like every week someone is coming out with another paper using spectral independence, or now generalizations that have grown out of it, to prove that some Markov chain is rapidly mixing. It's totally changed the field. Okay, I want to quickly tell you about one other thing Cheyenne has done. He's made many contributions to the traveling salesperson problem. So to understand this problem, imagine you're a tourist in a city like Philadelphia, and you wake up at your hotel and you want to visit a bunch of sites in the city, and then you're going to come back to your hotel at the end. So what do? You may take the sites, you make a little map, you write on paths between them how far apart they are, and now you try to find the shortest walk for your day. Let's say here it is. Now, if it's a small enough graph, you can do this. But when they're big, it's a hard problem. So the way we think of this in computer science is our input really is a graph with distances on edges. We know that it's NP hard to solve the shortest tour. That means we're not going to find a fast polynomial time algorithm that does this, always. We also know that it's NP hard to get an approximately shortest tour. If you want to get within about 1.008 of optimal, we know that's hard. Okay, then you should ask, well, if we just want to be approximately shortest, how well can we do? For a very long time, the best algorithm we knew came out of work of Christofides and Sergikov from the 70s that got within 3/2 of optimal. And the algorithm worked by finding a spanning tree that was as short as possible. That we can do efficiently. And then by adding some edges back to it. On a recent breakthrough with Carlin and Klein, Ovais-Garan came up with an algorithm that is a little bit better. It shaves that constant down by about 10 to the minus 36, they estimated in their paper. Probably they were being conservative. I mean, we could do a little more. But the point was not that anyone's going to be jumping up and down to shave off a 10 to the minus 36. The point is that the constant is not 3/2. We now know it's got to be something better. And we didn't know that since the 70s. And now all sorts of people are spending time trying to figure out, how do we figure out what this constant actually is? Also, the paper introduced some really cool ideas. I think it's a testament to what has been developed in the field that they could do this and to what they've developed. So one technique is, instead of using a minimum spanning tree, they use a random spanning tree. But it's not a uniform random spanning tree. It's sampled from a distribution that's determined by a linear program that was introduced by Held and Karp in the 60s. But they weren't trying to introduce a distribution on spanning trees, but that's where this is. They used some recent-ish developments in graph theory, the polygonal representation of approximate minimum cuts developed by Banksar and Gomans. And to analyze how their algorithm works and the properties of the random spanning tree, they observed that the random spanning tree has a strong Rayleigh distribution, and then they form the generating polynomial of that distribution. And these are known to be real stable polynomials, and they prove results about real stable polynomials, these properly fit within the geometry of polynomials, that are then what enable them to analyze the algorithm. It's awesome work. So if you want to learn more about Cheyenne and his co-authors' work, first, I didn't get it on the slide, but I see that both Cynthia Vinzant and Nima Inari are giving talks here at this Congress, so you can find them. Cheyenne's talk is happening today, here, at 6 p.m. So I hope many of you will come back for that. And before I leave the stage, first, I would like to thank Cheyenne for doing so much beautiful work, which has enriched my life, and congratulate him on a richly deserved award of the Abacus Medal.
Thank you very much, Dan. Fantastic talk. So please, Dan, the floor is yours.
It's a tremendous honor to introduce you to the mathematical world of Graham Siegel. The Chern Medal is an award for lifetime of achievement, and so I'll begin with some general words. So here's a timeline of some major themes in Graham's work. You see that he begins in the 60s with K-theory, equivariant K-theory, equivariant homotopy theory, classifying spaces, very much squarely in topology. He moves in the next period to configuration spaces. He introduces this scanning technique that he alluded to in the video. And then he turns in a different direction to the representation theory of loop groups. These are infinite dimensional Lie groups. And also to inverse scattering, integrable systems. And then since the late 80s, towards a geometric approach to quantum field theory. So along the way, of course, there are many, many landmark theorems. Here are some of them. The localization theorem and the completion theorem in equivariant K-theory. The first of these really part of the T-Singer index theorem story. The configuration spaces model for iterated loop spaces, his recognition theorem for infinite loop spaces using gamma spaces, and so on. The topology of spaces of rational functions, his classification of positive energy representations of loop groups, the Siegel-Wilson-Grassmannian, and then some results related to quantum field theory as well. But Graham's influence and impact really goes beyond these specific theorems, and it's about ideas, germs, points of departure that he introduces along the way. So these are ideas that developed and blossomed over a long period that originate with Graham. So one is the classifying space of a topological category, the idea that equivariant K-theory is related to geometric representation theory, his Burnside ring conjecture, and so on. The scanning technique, the Siegel axioms for two-dimensional conformal field theory, Floer homotopy theory, and so on. So I'm going to tell you about two of these, well, three of these, but the first two are grouped. But before I do, I'm still going to give a few more general remarks and in the following form. So I was recently asked, what type of mathematician is Graham? So that's a tricky question to answer what type of mathematician a given mathematician is, but here are some answers. So one is that Graham's goal, his motivation, is really to understand. And the new mathematics comes along the way in the process of understanding. Many others approach it, that's his locution, the other way around. He's a master at conceptualizing structure, at finding, this is what Yasha also alluded to, at finding the kind of right formulation that's going to lead to the right framing for the results. He penetrates really to the core of a mathematical idea. He's often ahead of his time. It takes a while for everyone else to catch up and understand his ideas. He's a marvelous communicator, and that explains part of his influence. He's also a very generous communicator. He shares his ideas and often leaves other people to develop those ideas. He's very geometric, has a very incisive geometric intuition, but of course he uses algebra analysis in all parts of mathematics. His mathematics is very elegant and innovative. And some of these qualities are really not, the evidence shows for Graham, the type that typically wins these kinds of prizes. Graham's also a very modest mathematician. And here's the beginning of several papers. And if you can read that on the screen, I think so, then you'll see that he tells that nothing original is in this paper. It was all due to Grothendieck or Atiyah or somebody else. That's a typical thing, but in fact, time shows that that's not at all true. And then there's the contemporary formulation, which is that Graham is the type of mathematician that will be the last to be replaced by AI. And I mean that in a specific sense. Namely, great mathematicians and great mathematics works at all scales, and often at all scales simultaneously. So at small scale, it's the art of crafting a beautiful argument, just getting the argument just right, accurate, and so on. And at the large scale, it's conceptualization of structure, looking around and introducing new definitions, new axiom systems, and so on. AI seems at the moment to have a cutoff, both at small scale and large scale. But that's a very dynamic observation. This is changing in time. It's changing very rapidly. But that's a subject for another talk. My subject today, Graham Siegel, has no such cutoffs. And now I'm going to tell you a little bit more specific about these two episodes in his mathematics that should illustrate these general ideas. So the first one is right at the beginning of his career in the topological stage. And it's when he was a graduate student. Graham was reading and trying to understand this paper of André Weil, very important paper, from 1951, in which André Weil gives a proof of the de Rham theorem. And Weil's proof is this, the following situation. So here we have a smooth manifold M, and it's given an open cover, a cover by open sets. And we make this double complex. So along this axis are the various intersections. Here are the open sets of the cover, here are the intersections two at a time, and so on. And along the vertical axis is the de Rham complex, the differential forms on the manifold. So there's a check differential in this direction and a de Rham differential in that direction. So Graham wanted to know how he could realize this complex geometrically. So what he does is, on the vertical axis, he replaces the de Rham complex by the smooth manifold M itself, and along the horizontal axis, he replaces this check cover by its nerve. So what is the nerve? Well, take a large dimensional real affine space and sprinkle some points, one for each open set in the cover. And now when there's a non-empty intersection of two open sets, fill in the line segment, or one simplex that connects them. If there's a non-zero triple intersection, then you fill in the triangle, or the two simplex that connects those, and so on. And so you get this kind of combinatorial object there. Now, one of the key ingredients in Weil's arguments is a partition of unity. So what's a partition of unity? Well, for each point of the manifold, you take a finite collection of open sets in which that point lies, and you write that point as a convex combination of those open sets. So in other words, for each point here, you get exactly a point of this nerve, which exactly consists of convex combinations of those open sets. So a partition of unity is a map from the manifold into this, into the nerve. And then Graham executes two moves that are very familiar in geometry. One is that we replace a function by a space. In this case, we use the graph. So we draw the graph of the partition of unity. And the other one is, instead of making a particular choice, we look at all choices at once. So he looks at the union of the graphs of these partitions of unity. So here's an illustration for two open sets with a non-zero intersection. If a point is in one of the sets but not in the other, then there's no choice. It just has to go to that point that corresponds to that open set. But in the intersection, we could have any convex combination, and so we get a whole interval's worth. So essentially, the figure we get is the original union of the two open sets, but with the intersection blown up. And that's already a beautiful construction. For example, you can use it to give a nice, elegant proof of the Mayer-V-Torus sequence. So I invite you to think about how that construction works with these very simple covers of the circle. Here's a cover with two open sets, but two components of intersection. Here's a cover with three open sets, like that. You can also consider examples with triple intersections, but it gets hard to visualize. So Graham takes one more step. He was thinking about this construction and also thinking about Milnor's classifying space of a topological group. And he unified those constructions by realizing this as starting from a category. And it's not a category as usually thought of in those days, but a topological category. That was a new idea, where the objects and the morphisms are not discrete sets, but can be non-trivial topological spaces. So here he makes a category whose objects are these intersections of these sets, but given the topology and the morphisms or inclusions, and he realizes this space, which is the classifying space of the category, by giving a particular construction that then unified that with Milner's construction. So this was all just an aside, just Graham understanding this Weil proof. It was an aside on the way to his PhD thesis. But he wrote it up. He was encouraged by Grothendieck to write it up. And the paper has been an amazing influence. It's a beautiful, really elegant paper, and I encourage you to read it. So on the small scale, this space that is constructed, we know what every point is. Every point we know in terms of partitions of unity. But Graham also thought of it on a large scale. And on a large scale, what we have is the homotopy type. That's what remains. And in fact, the projection to the space is a homotopy equivalence. So this idea of large scale of homotopy type really persists throughout Graham's work. He often finds homotopy types here for a category, a topological category, but in many situations. And I'll just say this quickly. He also, if the category has extra structure, then its classifying space will naturally have extra structure. And a structure you might want on the classifying space is an infinite loop structure. Those are spectra, which are the bread and butter of stable homotopy theory, which was being developed at the time. And so Graham invented this structure, which is called gamma space, or eventually Siegel space, which gives this infinite loop structure, and it led to a de-looping machine. And again, one of the main ideas is using this idea of homotopy type, replacing spaces by homotopy equivalent spaces to build this model. So these Siegel spaces, again, are very much in vogue in many contexts today. All right, so I want to turn to the second theme that I'll discuss, which is quantum field theory. And this dates from 1987. And here's the paper that Graham wrote. It was a preprint until almost 20 years later, I think, when it was published. And it circulated as a kind of samizdat preprint. People Xeroxed in those days, and everyone was circulating this preprint. And it's called The Definition of Conformal Field Theory. And again, he tells at some point that this is all known, and he's just kind of explaining it. But there are several things that came together that led to that preprint, and I like to think of it as Graham's axiom system for Wick-rotated quantum field theory. First, Graham had a long-standing interest in quantum field theory. When he went to grad school, that's what he wanted to study, but the field was in a very different state, not in this geometric state. In the 80s was the middle of a very important time in physics, in particular two-dimensional conformal field theory and its relations to loop groups, which he had just studied, and Riemann surface theory. He had done his work on loop groups, again emphasizing the more geometric group rather than Lie algebra, and his experience with categories and topology, as you'll see, also enters. So again, he was trying to understand, in this case, Ed Witten's 1986 ICM address, and that's what directly led him to this formulation. So let me first start by saying a little bit about axiom systems for quantum theory in general. Quantum mechanics dates from the late 20s or so, mid-20s, late 20s, and there were two different axiom systems that developed. The Dirac-von Neumann axiom system. And von Neumann developed the mathematics, functional analysis, spectral theorem, operator algebras, really in parallel with the development of quantum mechanics. And then there was another axiom system, Irving Siegel is associated with that more focuses on observables rather than states. Quantum field theory didn't have that kind of mathematical basis from the beginning. It was a few decades later that there are axiom systems in relativistic quantum field theory. So that means quantum field theory in Minkowski spacetime, Lorentz space, which is the setting of special relativity. And there's the Whiteman axioms and the Haag-Koestler axioms. Graham's has to do with the Wick rotation. So let me say quickly what it is. In quantum mechanics, there's a state space, which is a Hilbert space, a complex Hilbert space. There's an algebra of observables, which are the operators on the Hilbert space. And there's a unitary evolution, a one-parameter unitary group that tells you how the system evolves, how the states evolve. It's generated by the Hamiltonian, whose spectrum are the energy of the system. So if that spectrum is bounded below, let's call it a positive energy condition, then in fact you can make this complex semigroup. So this is in fact a holomorphic semigroup in this lower half plane. And the boundary values of that is the unitary evolution. And now you can restrict to this real semigroup here, and that's the Wick rotation, passing from this unitary one-parameter real group to this semigroup of contractive operators. In quantum field theory, there's a similar Wick rotation. Think of correlation functions, which starts in Minkowski spacetime. Again, there's a complex domain, and then one ends up in Euclidean spacetime, having made time imaginary. And then we could imagine trying to go, as we do in differential geometry, from Euclidean space to curved Riemannian manifolds and contemplate doing quantum field theory there. So that's the arena in which Graham's axiom system lives. So the axiom system, it has a dimension n, which is the dimension of space-time where we not Wick rotated, and some structure, local structure on the manifolds. Think of Riemannian metrics, for example. But it might be a topological structure as well. And he makes a category whose objects are closed n-1 manifolds with this structure, and the morphisms are Bordisms from between these closed n-1 dimensional manifolds. And his axiom system is a very simple statement that a field theory is a linear representation of that Bordism category. So it's a homomorphism, meaning compositions of Bordisms go to compositions of operators, and also disjoint unions go over to tensor products. And that's it. So needless to say, that's very far from the way quantum field theory looks if you open a physics textbook. But that's not so unfamiliar in mathematics. We teach every undergraduate math major 3 magic words: complete ordered field. And those words don't really look very much like the real numbers that we learned in school. But that's a kind of conceptualization of structure. So in Graham's case, well, the Bordism category has this real semigroup in the one-dimensional case, which is quantum mechanics that we saw. These are Riemannian intervals that go over to these operators. There are semigroups in these higher cases as well. So this axiom system gave mathematicians an entry point into quantum field theory, in particular to geometric aspects. And it was rapidly generalized, and lots of extended, lots of different developments around it. And the almost 4 decades since Graham introduced that have borne out that he really put his finger on something important, because the structure has occurred in many places in mathematics. In low-dimensional topology, symplectic geometry, algebraic geometry, geometric representation theory, the Langlands program, both geometric and algebraic aspects, and so on. And there's been feedback into theoretical physics as well. So this is still very much something in progress, and the story is not yet written. So let me conclude with just a brief remark about Chern and Siegel. Graham was a graduate student initially at Cambridge. He was a student of Hodge, and then he moved to Oxford to work with Michael Atiyah. And one of the first things that Hodge told him was to read Chern's papers. So he started reading about Chern classes and Chern, Gauss-Bonnet, and so on. Both Chern and Siegel are profound geometers whose ideas are really embedded into the very fabric of our mathematics. And I think for that reason, Graham is a terrific recipient of this year's Chern Medal. Thank you.
Thank you very much for very beautiful talk. Stefan, yeah, floor is yours.
Thank you. It's my pleasure to give the Laudatio talk for Yuri Nesterov, who's the winner of the Gauss Prize. So Yuri has made fundamental contributions to optimization. And because of the very broad reach of optimization, his work has influenced many application fields as well. He mentions several in the movie, including training of machine learning and AI models, which has become a real happy hunting ground for optimization methods. Yuri has shown how to utilize information and structure inherent in certain important classes of problems and leveraging this information to design and analyze novel and efficient algorithms. He has changed the way that we design, analyze, and even think about optimization methods. So the Gauss Prize recognizes mathematics with significant impact beyond mathematics. And as I mentioned in the first slide, optimization is an area with very broad reach. And so if you make advances in optimization, you're likely to affect many fields. I'm going to talk about 5 aspects of Yuri's work over the last 40 years, but they sort of follow a common theme. So first, he looks at, for a given optimization problem, what kind of mathematical structure is present in that problem? How smooth are the functions involved? Are they convex, non-convex, and so on? Secondly, what information is available for the algorithm to use? So for example, can the algorithm access gradients of a function or just function values, or maybe Hessians as well? Or maybe you can only get some sort of estimate of the gradient. And given those ingredients, how can you design an algorithm and prove its performance, prove things about its worst case behavior, possibly even prove that it does the best possible job using the information available? Sorry, I'm trying to advance. Here we are. Here. So here are the 5 things that I want to touch on. The first one was mentioned by Yuri in his talk. He called it the fast gradient method. The second one is some work with Arkady Nemirovsky, his great collaborator, on interior point methods. Third, the smoothing technique that Yuri also mentioned in his movie this morning. Fourth, cubic variance of Newton's method. And lastly, his recent work on higher order tensor methods. A little bit of biographical information, also mentioned in the talk. Yuri obtained his PhD in 1984 from Moscow State University, subsequently worked at the Central Economic Mathematical Institute, but has spent most of his career at Louvain-la-Neuve since 1993. He became emeritus there in 2021. So let me start with the fast gradient method. So this is simply unconstrained minimization of a smooth convex function. And using only first order information. So the information available is that at any point you can evaluate the gradient of the function. And it's smooth in the sense that the gradients are Lipschitz continuous with Lipschitz constant L. So maybe the most obvious and natural first order method is to simply move at any given point, the point that you're currently at, move in the negative gradient direction. And so that formula on the left there is the kind of most fundamental first order method. You notice that there's a step length there of 1 over L, where L is that Lipschitz constant for the gradient. It's very easy to prove using just a few lines of analysis that that step is guaranteed to give you an improvement in the function value. F of xk plus 1 is strictly better than f of xk, provided you're not already at a minimum where the gradient is 0. And in fact, you can show, again, just using a few lines of analysis, that the gap between f of xk and its optimal value decreases like 1 over k for each, where k is the iteration number. And you can do a very simple flip to say that the number of iterations you need to reduce that gap below epsilon is going to be order 1 over epsilon iterations. So that's kind of the obvious thing to do, but Yuri asked, can you do better just using gradient information and just using one gradient evaluation at every iteration? Can you potentially get a better rate? And the answer is yes. And the formulas are given on the right there. So now instead of one sequence of iterations, we've got two. We've got the xk and an auxiliary sequence yk. You get the next yk by taking the latest xk iterate and continuing to move in the step that you just took, the direction that you took in moving from xk to xk plus 1. You keep going in that direction. So it's kind of a momentum idea. So that gives you the next yk. And then to get the next xk, you simply take a gradient descent step from the yk. So it's not obvious why that should work, and the analysis is also not obvious. Uses a Lyapunov function type argument, but the upshot is that the gap between f of xk and its optimal value now decreases like 1 over k squared rather than 1 over k. And so in order to get that gap below any tolerance epsilon, you only need order 1 over square root of epsilon iterations. So this idea of momentum had been around in the 1950s. Conjugate gradient had been invented. The Russians invented in the 70s the so-called heavy ball algorithm, which also used momentum. But you could only prove, in those cases, you could only prove convergence for convex quadratic functions. And Yuri showed by this expedient, by slightly changing these methods, that you could get a proof that worked for general smooth convex functions as well. And so that simple idea, as Yuri said, that was kind of ignored for many years, and then suddenly it was sort of rediscovered much later, after he'd already become famous for his work on interior point methods. And it turns out to have an enormous range of applications. You can extend it to methods called coordinate descent methods, where you just change a few components of x at every iteration, only a few components of the vector. It's got applications in composite functions, where you've got a combination of a smooth function and a potentially non-smooth function, such as you see in compressed sensing and a lot of image processing problems. It's got applications in saddle point and variational problems that arise in equilibrium and game theory. And as Guri mentioned, it's got applications in statistics and machine learning. So this idea of momentum is used almost universally in training neural networks. So Yuri calls it the fast gradient method. It's probably better known in the community of machine learning and optimization as Nesterov accelerated gradient, or simply Nesterov's method. Secondly, interior point methods. So in the 1980s, there was sort of a revolution in linear programming when Kamaka came along and presented a new method with polynomial complexity. And there was a lot of work in sort of extending and modifying and that, simplifying it to some extent. That sort of reached maturity by the early 90s. But Yuri and his collaborator Arkady Nemirovsky looked at the more general problem of minimizing a linear function over a convex set K. And this idea of a barrier had been around since the 1950s. So the idea of the barrier is you define a barrier function related to the set K, where f takes on finite values in the interior of K, but it goes to infinity as you approach the boundary of K from the inside, and it's not defined on the exterior of K. And so the idea is you replace that original problem with an unconstrained problem, in a sense, that consists of a linear combination of the original objective, C transpose X, and this barrier function. And the parameter t in this combination you drive to infinity. And by changing t and finding the minimizer inside K of that function there, you can trace out a so-called central path. And as t goes to infinity, you approach the solution of the problem, which is usually on the boundary of K. So the trick is, how quickly do you increase t? How do you turn this into an algorithm? Well, you increase t at a certain rate. At each value of t, you take a few Newton steps, and you restrict the step length of the Newton step so that you don't leave the set K. And you have to put that all together in just the right way. And so the big contribution here was to define some properties that you want this barrier function to have. So barrier functions were already known. Frisch in the 1950s came up with the idea of a logarithmic barrier function. His formula is given there on the right. But the key property turned out to be this property of self-concordance, which is given by that first formula on the left there. And basically, self-concordance says if you take the third derivative of f along a particular direction h, it's bounded in terms of the second derivative of f along the same direction h, to the raised to the 3/2 power, with this magic constant 2 in there. He also defined a barrier parameter, and that's defined in that second formula, which says that, again, the gradient of f operating on a direction h squared is bounded by nu times the second derivative of f operating on h. So you pick a mu so that f satisfies that property. So using that value of nu, and using, as I said, a systematic way of increasing t at each iteration, and then taking several Newton steps within each iteration, with certain step lengths, you can show that overall you can get a solution that's accurate to within epsilon of optimality in that many Newton steps, or the square root of nu times log 1/epsilon. And so this turns out to be applicable. It turns out that you can define barrier functions f with this property for some very important classes of constrained optimization problems, linear programming being one of them, but also quadratic programming, also matrix optimization problems where the unknown is not a vector, but it's a symmetric matrix that you want to be positive semi-definite at the solution. The barrier function for that is the negative log of the determinant of x. And you can also extend it to other problems in so-called second-order cones. And this has enormous reach. Semi-definite programming turns out to have applications in control, engineering design, statistics. It's also used in combinatorial optimization to give provable upper bounds on important combinatorial problems. The third one, exploiting the structure of non-smoothness, and this is something that Yuri mentioned in his talk, where he said he had two papers on his desk that seemed to talk about two completely different things, and he managed to put them together. Well, the key observation here is that many interesting problems where f of x is non-smooth define x in this way. The maximum of a times x for some matrix A in a product with u minus a convex function phi of u, and you maximize that over u belonging to some convex set. And it turns out that for many choices of the function phi, you get interesting problems, interesting non-smooth problems. So his expedient was simply to round that, to smooth that function out by introducing inside the max, introducing another strongly convex function d of u and a parameter mu. And so by just redefining the max over that slightly modified function, you get a smooth surrogate to the original problem. And now that you've got a smooth convex function, you can apply all the machinery of, including the Nesterov accelerated gradient that I mentioned at the start. You can apply all that machinery to get rapidly convergent methods. And that again turns out to have this enormous range of applications in imaging problems, matrix games, network models, robust optimization, and so on. The fourth one, this is from about 2005 with Nesterov and Boris Polyak. So it's well known that Newton's method is widely used in scientific computing. It's a very rapidly convergent algorithm, and it's very simple to motivate. You simply replace the function f that you're trying to minimize at any iterate with its Taylor series quadratic second-order Taylor series approximation around that iterate using the function value, the gradient, and the Hessian at the iterate xk. So it's well known, unfortunately, also that there are worst case functions k where the behavior of Newton's method is as slow as the first order method. So the idea that Nesterov and Boris Polyak had was to add on a regularization term, this third order term, in d cubed, where d is the step that you're taking away from xk. And the coefficient in front of that m is the Lipschitz constant for the Hessian. So it turns out that if you get the step not by simply minimizing the quadratic, but by minimizing this cubic term, you can provably get to a point where the gradient is less than epsilon in at most order epsilon to the minus 3/2 iterations. And of course, you're looking for a point where the gradient is 0, because that's a so-called stationary point for a non-convex problem. So that's for the non-convex case. In the case where f is convex, you again get an acceleration in the convergence rate over the standard steepest descent method or first order method. So this sort of started a whole revolution in complexity theory for second order methods. Up until that point, there was very little work done on that, but this started a whole bunch of people, including myself, looking at complexity theory for higher order methods. And finally, this is the most recent work of Urey, where he goes beyond a second order approximation that's used in Newton's method to third and maybe even fourth and higher order approximations. And so the function phi of x and p there represents a p-th order Taylor series approximation around the point x. And to that he adds a regularization term. So very much in the spirit of what happened on the previous slide, except that now instead of being a cubic term, in general, it's a p+1 order term. And the key observation here is that if you make the constant in front of that p+1 order term big enough, that whole subproblem is a convex problem. And so it's a tractable problem. So you can solve the subproblem that you need to solve to find the step tractably using your favorite machinery for convex optimization. And so he's been able to describe p-th order themes that in general take order of k to the minus p+1 iterations to converge. So I've mentioned 5 things, 5 advances. They all make use of the structure of the problem at hand. And they all, again, result in algorithms that were very novel and had a guaranteed complexity theory. So I've mentioned in talking about each of these things that the math that Urey has done has influenced optimization very deeply, but through optimization it's influenced an enormous range of areas, and I've captured several of them there, and I've mentioned them during the talk. And particularly I want to highlight again machine learning. So the impact's not in a single algorithm, but it's in the whole approach to designing and analyzing algorithms. So again, Urey has taught us to ask, given the information available and given the structure of problems, what's the fastest, what's the best way to define efficient algorithms? And his algorithms have reshaped optimization theory, transformed optimization, and reached far beyond mathematics into a whole range of applications. So congratulations to Guri on the Gauss Prize.
Thank you very much, Stefan. So, Carola, please use your turn.
Okay, good afternoon, everyone. It's my great pleasure and honor to be giving this Laudatio for Hannah Fry, who has received the Lilavati Prize this morning. So let me start by saying a few words about the Lilavati Prize. It has been awarded for the very first time in 2010, and since then every 4 years at the ICM, with Hannah being the 5th recipient today. And you see previous award winners here in this timeline. The name Lilavati comes from a celebrated 12th century Sanskrit mathematical treatise by Bhaskara II, which presents arithmetic and algebra through verse problems addressed to Lilavati, which we believe has been Bhaskara's daughter. So it's a beautiful piece, it's a beautiful example of mathematical exposition. And that's also why the IMU uses this name to honor the long global tradition of public communication of mathematics. Now, I'll start talking about Hannah by focusing on a few milestones throughout her career. Hannah is the professor of the public understanding of mathematics at the University of Cambridge since last year. She's the very first holder of this chair at Cambridge. She's also the president of the Institute for Mathematics and its Applications since 2024. And of course, She is one of the most internationally renowned mathematical communicators in the world. Her career started at UCL, where she did her PhD in 2011 on the study of droplet deformation. And from that time onwards, she went up the career ladder, went up the ranks at UCL, starting as a postdoc in 2012 in a project called the Mathematics of Cities, which was also the time when she started public communication, public lectures on the research that she did there. And I'll talk a little bit more about that in a moment. In 2015 was also an important year because this was really the year where her public communication reached a breakthrough, and the TED Talk on the mathematics of love was mentioned also in the video, which then also led to a book and many more books that I will also say a little bit more about later. So this TED Talk really went viral at the time and kicked off her career as a public communicator. She then accumulated several accolades over the years. I'll just mention a few. In 2018, she received the Christopher Seaman Medal that is jointly awarded by the London Mathematical Society and the Institute for Mathematics and its Applications for her work in public engagement. She delivered the Christmas lectures of the Royal Institution in 2019, which I will also say a little bit more about in a moment. And in 2022, she has been elected as an honorary fellow of the Royal Academy of Engineering. So Hannah is an applied mathematician by training, working on the development of models for spatial interactions, modeling spatial interactions and collective behavior. And this example on a discrete spatial interaction process that she developed was part of her work during her postdocs in this Mathematics of Cities program. And I've chosen that because it, first of all, marks the start of her public outreach focus. It also demonstrates that what she uses in her outreach work grows very often from real applied mathematics research. The topics that she chooses are topics that people care about. She touches upon nerves of people by hitting topics of current public interest. And the third is that Hannah's message always is that mathematics is human, not just in the sense that humans are doing mathematics, of course, but that humans are using mathematics in their everyday life. And this is always something that she highlights in her work. Now, another very, very, I think, special feature of Hannah's work is that she reaches extremely broad audiences that go well beyond the typical math outreach audiences that we are used to. A good example for that are the Christmas lectures of the Royal Institution that she was giving in 2019. These lectures have been founded by physicist Michael Faraday in 1825. And Hannah was only the second mathematician ever delivering them, with Christopher Seaman being the first one in 1978. And she did a tremendous job doing that. These lectures are broadcasted on BBC. More than 2 million viewers on BBC. They're also now available on YouTube, and I very much invite you to watch them if you haven't done so. They're really entertaining. And also on YouTube, they reached more than 600K views. And how she opened these lectures is, I think, also a very good example to bring across the way she talks about mathematics and how she captures the attention of the audience, which is through a life experiment. So she started her lectures with a life experiment demonstrating this capstan effect, which involved a plastic bag of greenish gunge that was attached to a string hanging above stage. The string was running over a cylindrical rod, which is this grayish thing in this graphic. T load is the greenish gunge hanging there. And then at the other end of the string, there is a small weight, it's called T hold. And what she wanted to demonstrate was that if you now let the string loose on the side with a small weight, that if you chose the small weight appropriately, following this equation that you see here at the bottom, it will create just enough friction for the string to wrap around the cylindrical rod to hold the greenish gunge and hinder it from splashing onto the stage and covering everyone in this greenish liquid, right? And so it's a good example. You know, it's hard, by the way, to give a laudatio for someone who is excellent in math communication. You really need to watch these lectures. What she did there was really to first, and this is something she always does, she first introduces the problem, motivates the people to really wanting to understand why did this work, but also she played with the suspense of the moment. And again, this is always her link to the human nature of, well, of course, you know, we kind of believe that this will work. I mean, she wouldn't do this on stage if it wouldn't. But there is it's just in human nature that we worry about it. But, and this is something she says then also in these lectures, mathematics gives you a way to be sure about things. Yeah? And this also nicely came across, I think, in the video where she talked about her own cancer story. It gives you objectivity, and this calms you down. Now, apart from these Christmas lectures, Hannah does a lot of work for the BBC. This is just a few examples of the body of work that she has been doing. The common thread is always that mathematics is presented as a way of understanding decisions embedded in ordinary life. And I'll take one of these BBC contributions as an example to show you that the impact actually goes even well beyond outreach, which was a BBC documentary that she hosted in 2018 called Contagion, which was a documentary about pandemics and epidemiological modeling, paired with a citizen science project that she jointly performed with the London School of Hygiene and Tropical Medicine, where she recruited more than 50,000 volunteers from a town in Surrey in the UK called Haslemere to be tracked, to track the movement and contact data over 3 days. And so this data was collected. So now, apart from the outreach impact this had, this data also, first of all, had an impact on research because it was used subsequently by mathematical biologists to develop new models. And here I've given as an example the work of Julia Goggins and colleagues. But also at the time when the COVID-19 pandemic hit us, which was kind of 2 years after, the data and the models derived from this data were used to inform the UK government COVID response, filtered through to the government by the scientific advisory group called SAGE for emergencies at the time. So I think that's really remarkable. So now, why does the public listen? And again, you really need to watch her contributions if you haven't done so yet. I think in just one sentence, Hannah has this really wonderful ability to talk to the ordinary person on the street at their level, let's say. So she has this ability to turn mathematics, mathematical explanations into ordinary language, and to capture the attention of the public by introducing problems that are very close to them. And she has a lot of charisma as well. And now how is she doing this? The interesting thing is also that she uses various types of media. So she has written 4 best-selling books so far. The Mathematics of Love we have mentioned before. Another one to mention is Hello World, which was also part of the citation for the Christopher Seaman Medal that she received. And also for which she received the 2020 Asimov, the 2020 Asimov Award. And these are books that have been translated in 15 different languages. So is a tremendous reach that she has here. And then this is not the only thing she does, right? So she's in television, she does radio, podcasts, social media, streaming platforms, public lectures, you name it. And so here are just a few examples. And with Stephen before, we've talked about Rutherford and Fry, which is really a wonderful podcast. You should, again, listen to it. Now, with the Christmas lecture, I've started with a Christmas lecture of wanting to highlight also the reach that her math communication has. I think this year, everything that she has done so far will be topped with respect to this, because she is going to be part of the 2nd season of the Celebrity Traitors, which, for those of you who don't know what the Traitors is, I actually didn't, I have to say. It's a reality TV show, which is a social deduction game where a group of people comes together. Most of them are faithful, but a few are traitors, and they need to be identified and need to be voted out. And so, first of all, you can imagine, this is actually super popular, not just in the UK, but in lots of countries. So reaching audiences that, we usually really don't reach, so massive in that respect. But it's also a game full of mathematics, potentially. So it's, hidden states, incomplete information networks, strategic inference. So a lot of this she can use to advantage, and of course also changes the public image of what a mathematician is. Now, Hannah is, someone who is great in outreach, but she also comes with a lot of credibility, both to the public as well as to us here in the room, to her fellow mathematicians, because she's in a lot of leadership positions as well in academia. And here I've just repeated some of the things that I've shown you, that I've already shown you before. So why was Hannah Fry chosen as a Lilavati laureate? Of course, I haven't been in the committee, but I can tell you what I think. I think these are really the four pillars of what makes her so impressive. It's the range of things that she's doing. Books, TV shows, podcasts, public lectures, and so on and so forth. It's the way how she can really turn mathematical substance in something graspable to, to an ordinary person on the street. It's the way how she engages with the public, hitting the nerve of what people are interested in. I think in the video, again, a wonderful example was the one with the taxi driver during the pandemic. She explained exponential growth to him. And it's a representation, a mathematics professor is an expert, visible, warm, funny, and recognizably human. So I'll finish by saying Hannah Fry has shown that mathematics can be public without becoming simplistic, personal without becoming anecdotal, entertaining without losing evidence, and rigorous without losing humanity. So really congratulate Hannah for this wonderful honor, and I thank her for bringing mathematics to the public with rigor, warmth, courage, and joy. Thank you very much.
Thank you very much, Carola. So let us thank all the Laudatios speakers in this session. So this concludes our afternoon activities. We look forward to seeing you all this evening and throughout the week as we continue to celebrate mathematical greatest achievement. Thank you very much.